I will talk about this project OptiRoll, which is going to finish by end of this month. The goal for this project has been to develop a tool for optimization of long products rolling. And the task we were up to, the challenge we were put up to, that this tool should be easy to use. It should require very low knowledge threshold. It should compute reasonably fast, as well as it should be sufficiently accurate. Uh, so the task which we did in these projects, first one was the material characterization. 5 different materials were selected. Those were typically the most difficult ones in each of these 5 companies to roll. One task was typically in the rolling of high-speed rolling. You can say the strain rates we encounter are quite high, so we needed to do the split Hopkins pressure bar high strain rate testing, and temperatures were up to 1200 degrees Celsius, and strain rates are up to 5000 degrees Celsius, 5000 per second. The low medium strain rate were from 1 to 100 per second, and that was performed by at Keymub using Gleeble, plus we did some characterization using EBSD. Again, the same temperature for up to 1200 degrees Celsius. So altogether we had measurement data from 1 per second to up to 5000 per second up, and temperatures from 900 to 1200 or 1250 some cases. Migdal is one software tool that is being developed at Keymub, and that is being used in the project, and it has been provided to all the project partners. It is being used as a database to store all the results from testing, as well as a predictive tool for microstructure properties. Here you can see a snapshot of the tool. After this, for modeling purposes, we calibrated the tool, calibrated the Johnson-Cook model between 900 to 1200 degrees Celsius for all the strain rates. And this model has been used in the process modeling. Rolling process simulator. This is another tool. It's called RollSim as well. This has been also developed in the project, and that's implicit finite element code, which is based on 2.5D or generalized plane strain. It's a nonlinear elastoplastic. It has nonlinear elastoplastic material with large deformation and rotation. We have to implement the remeshing as well as mapping of results between different meshes, as well as it's available on Windows, Linux, and Mac. Here is a demonstration of the software. It shows this is a material selection. Here you choose the number of passes, and you can see entering the different parameters for each pass. It's a screen capture, and so it takes roughly 120 seconds to put in all the data, calculate, and see the results. One of the highlight of this is how easy it is to use. You don't need to know anything about simulation. It's only entering process parameters and selecting the material. We have a possibility of different tools. Here what you show is alternatively oval and round, but you have also a flat rolling as well as square tools are also included. And here you see the initial properties, that's initial temperature, initial radius of the wire. Here is the ingoing velocity. We have the possibility to give different initial cross sections, typically like round, oval, or square. Now it's calculating. What you see here is the stats from the simulation, and you see we are in pass 4, increment 5. So typically one pass is calculated by 5 increments. In this case we are in pass 6, and you see Here is the computer result. You can also slide through individual increments or passes, and here is the final plotting velocity. So we have the tool, and that tool has been validated with plant trials at 4 different plants. What we did there was we took cross sections after. This is before it goes into the finishing block, and this is at pass 1, after pass 2, pass 3, pass 4, pass 5, and pass 6. What we could measure there is the geometry, how it comes out of each after each pass, and this could be validated with the simulation. So here you can see 1 or 2 of those type of comparisons. Here is a 6 pass finishing pass, and here is a 8 passes, so 2 different materials. And the round is measurements, and then you have the simulation, which is the continuous line. And these denote the large and small dimensions of a wire when it passes through oval and round. So to conclude, what we achieved in the project is we developed a tool which is quite easy to use. I think you could appreciate that. It doesn't require any knowledge about materials or simulation to be able to use that. Computes reasonably fast and is sufficiently accurate. It's been compared with general purpose code mark as well as with plant trials. It helps us to explore new solutions for plant layout. You could try different roll profiles, and the main part is to avoid the critical temperature in the wire cross section, so you don't form pores or defects while rolling. We also have a possibility to compute the microstructure by exporting the data from RollSim and put it as an input to the MIGDEL software from KeyMap. So that's the status.
Tack så mycket. Som vanligt, är det någon som har en fråga så tar vi gärna den. Ja.
Did you ever try to introduce that you have a non-homogeneous material that you have, for instance, a segregation, how that would influence? Could you sort of mesh up that?
We have not done that, but I don't know really how to model segregated materials right now. So far I haven't seen anybody successfully doing it. But on the other hand, for your case, modeling of inclusions, that could be done in, so inclusion, pores and so on, that we can calculate, but segregation, I have no clue.
Can you put in initial as a square? Also, can you start?
That's possible. Okay. So you can give the initial cross section either as a round, in this case which I showed, or it could be an oval or a square.
Okej, tack så mycket.